Hi guys, this is Avery Morgan. I'm doing the test for extra credit video. So with that, let's go ahead and jump into number one. Find an organic compound with three or more functional groups that contain an oxygen-containing functional group, nitrogen-containing functional group, and one other functional group and name them. Also, for every atom in the structure, identify each atom's electric geometry, molecular geometry, and hybridization. So no repeats. Well, I'm the only one doing this, so I don't gotta worry about that. After a lot of internet scouring, I found serine to be our organic compound with three functional groups. So for part one of one is identify the functional groups. Well, first thing we need to do is identify the parent carbon structure or backbone so that we don't accidentally mix it up with our functional groups. So we go ahead and circle the parent. This isn't absolutely necessary. It's just something I like to do. So there's our parent. So now for our functional groups, we have pretty much any of the quote unquote branches um that aren't just carbons and hydrogens. So we have, oh, I'll get funky on me. We have one here. We have one here. I'm going to do them in different colors. We have one here, here, and we have one here. Oh, that's not a different color. One here. Okay, so now all we have to do is name these functional groups. Thankfully, Professor Byan has provided us with an amazing function group chart from our notes. It is on page 2 of chapter 3 notes. And with that, you just look down the chart and figure out what the functional groups are. So for OH, this is going to be alcohol. For the NH2, if you look under the nitrogen containing compounds, you see NH2. That is a amine. Amine. Thankfully, this is not a verbal test. So then amine. Maybe let's try that with slightly better handwriting. And then final one, which is a carbon double bonded to a oxygen double bonded to a carbon that also has an alcohol uh bonded to that same carbon. That is what is called a carbo carbolic acid. So that's how you identify your three functional groups and naming them. Now we have to identify every atom in the structure with all of its fun geometries. So, oh my lord. Okay, for the next one, we have, I'll circle these in purple. We have an atom here, an atom here, an atom here, an atom here, one here, and one here. So I'm going to go ahead and label these with letters so that when I go around and do them, it's easier to identify. So we have A, B, C, D, E, and F. So now let's start with A. For A, we have an oxygen bonded with a hydrogen and to a carbon. That oxygen has two lone pair electrons. So the electron group is going to be 4 because we have two bonded atoms and two electron groups. So 2 plus 2 is 4. Now that we have our electron group, we can go ahead and answer what the electron ge geomet electron geometry is. And since we have 4, it's going to be 109.5 degrees tetrahedral. Now for the molecular geometry, since we have two lone pair electrons, the molecular geometry is not going to be tetrahedral. Instead, it is going to be bent because I didn't quite draw this well. Another way to draw this is like this. And so now you can see more of that bent shape. And then lastly, for hybridization, I can spell hybrid. We have 4 for our electron geometry, so we use the hand trick, STPP. So we have S and 3P, so it's going to be SP3. Let me go ahead and just make a little bit of space there. And now we are going to do B. B is a carbon bonded to a hydrogen, hydrogen, another hydrogen. That's actually an oxygen, and another carbon. So we have 4 bonded atoms and 0 lone pair electrons. So our electron group is going to be 4. So with that information, we can now answer the rest of it. Our electron geometry is going to be 109.5 tetrahedral. In our molecular geometry, since we have 4 bonded atoms and 0 lone pair electrons, it's also going to be tetrahedral. And then our hybridization, again, since it is electron group of 4, it's going to be sp3. Mm. So now let's move on to molecule C. I don't know where I want to put this. We'll put this here. Molecule C. We have a carbon bonded to another carbon, bonded to another carbon, bonded to a hydrogen, bonded to, and bonded to a nitrogen. So we have an electron group of 4. So now our electron geometry is going to be 109.5 degrees tetrahedral. Our molecular geometry is going to be tetrahedral. And our hybridization is going to be sp3. Awesome. I'm going to go ahead and make this all smaller so you can still see it, but I kind of need it out of my way. Cool. So now moving on to molecule D. We have nitrogen, which is bonded to 2 hydrogens, a carbon. So we're going to have a lone pair of electrons because all of these atoms follow the octet rule, or at least nitrogen does. So since nitrogen follows the octet rule, we have to add that lone pair of electrons. So our electron group is also 4 because we have 3 bonded atoms and 1 lone pair, so 3 plus 1 is 4. Our electron geometry is going to be 109.5 tetrahedral. Our molecular geometry, though, is going to change because we only have 3 bonded atoms. So our molecular geometry is going to be trigonal pyramid. And then our hybridization is going to be sp3. Now moving on to molecule E, we have a carbon double bonded to an oxygen, bonded to a carbon, bonded to another oxygen. So our electron group is going to be 3. Please do not count the number of bonds. We are counting the number of bonded atoms. In this case, we have 3, the 2 oxygens and the carbon. Since we do have a total of 4 bonds, we are going to have 0 lone pair electrons. So 3 plus 0 gives us 3. Electron geometry, because it's 3, is going to be 120 trigonal planar. And then our molecular geometry is also going to be trigonal planar, again, because we have no lone pairs on this guy. And our hybridization is going to be sp2. Again, we're going to use the same trick with the hand. Our thumb is going to be S, pointer finger's going to be P, middle finger is going to be P. So that leaves us with 1 S and 2 Ps. Awesome. So now we are on our last one. Oh, no, it's not what I was asking you to do. You're going to do molecule F. Molecule F looks like this. You have a oxygen, a hydrogen bonded to a carbon. This is the exact same as A. So we already, since this is the exact same as A, we know that the electron group is going to be 4. Our electron geometry is going to be 109.5. Our molecular geometry is going, electron geometry is going to be 109.5 tetrahedral. Molecular geometry is going to be bent again because with the 2 lone pairs, it gives us this shape, bent or V shape. And our hybridization is going to be sp4. Awesome. And that is how you do the first question. Question number 2. Draw and name constitutional isomers for C4, 7H7Br. So this is 4 carbons, 7 hydrogens, and 1 bromine. I went ahead and took the liberty of drawing the skeleton of it all just to save some time, but I do want to go ahead and explain. You're going to see a lot of cyclones on here and not the up and down zigzags. And the reason for that is if is because if we were to draw 4 carbons with this zigzag shape with the bromine on it, when we count up the hydrogens that would be on here, we would have 1, 2, 3, 4, 5, 6, 7, 8, 9 hydrogens on here. and that is not how many hydrogens we have. We only have 7 hydrogens. So we turn to the cyclones because when we do the cyclones, get this out of the way. When we do the cyclones, for example, if we're looking at cyclobutane, when we have our square with a bromine, we have 1, 2, 3, 4, 5, 6, 7, which is the exact amount of hydrogens we need. So with that in mind, let's go ahead and look at the skeletal structures I already drew out for us. So the first one is going to be a square because that gives us a bromine here. And then we have here, I will label hydrogens in blue and carbons in green. That gives us 1, 2, 3, 4 carbons, and as I just drew out before, 7 hydrogens. Now we have to name this structure or this isomer. We have, since there's only one branch, we go ahead and assign that at 1. And the branch, okay, let's backtrack a little bit. We identify the parent, this square, aka uh cyclobute is our parent because it is the longest uninterrupted chain of carbon. It's also the only chain of carbon. And then we have our branch. So our parent, as I've already been saying, is going to be cyclobute. And then our branch is bromo because we have one bromine and it's located at 1, so we do 1 dash bromo. Since there are no functional groups on this isomer, we end the name in A and E, so it gives us 1 dash bromo cyclobutane. Yes, making sure I spelled that correctly. So now moving on to the next one, um, we have our parent. Well, first let's identify how many carbons we have, just to make sure we're right here. We have 1, 2, 3, 4 carbons, and 1, 2, 3, 4, 5, 6. Oh, yes. I'm sorry. This is only one hydrogen. So 1, 2, 3, 4, 5, 6, 7, which is perfect. And then we have our bromine right here. So now we've identified that this is correct with the chemical formula we've been given. We can go ahead and circle the parent, which is the longest uninterrupted chain of carbons. Right here, over here, we have 1, 2 carbons, and then it gets interrupted with the bromine. And then in our triangle, we have 1, 2, 3. So this is going to be our parent. And then this is going to be our branch. Our parent is a cyclo prope. We don't know the ending yet, so we can't put that on there. Cycloprope. And our branch has 1 carbon and 1 bromine. all attached to the one. So it's going to be one dash, one singular carbon, which is going to be methyl, because meth is the prefix for one, and it's a branch. So it's going to have the it's going to have, like I was saying, this right here is going to be our our methyl, because it's a singular carbon. And then right here is going to be our bromo, because it is a singular bromine. And the O is the suffix for one, and the meth is the prefix for one. And the YL, the ol, is the suffix for branch, because there are no other functional groups attached to it. Ah. So, since this is all attached to the one, oh, I did not mean to erase that. Whatever. Ignore the two there. So this is all attached to the one right here. It's going to be one dash bromo, because it comes first in the alphabet, methyl. So now we put it all together, we get one dash bromomethyl cyclopropane, because we have no functional groups attached to this. So this brings us to the next one. Let me make some space. Which is this crazy thing. Again, the longest chain of uninterrupted carbons is going to be this triangle, which becomes our parent. And as we know from the previous one, is going to be a cycloprop. And now we have two different um two different branches. We have 1, 2, and 1, 2. So the only way, oh, let me circle our branches. Branch here, and then I'm going to throw our bromine right here. We have another branch here. So for our branches, we either have 1, 2, or 1, 2. Since they're the same numbers, we have to go alphabetically. Like we established before, a single carbon branch is going to be methyl, and a single bromine branch is going to be bromo. Bromo uh, alphabetically becomes before the methyl. So the order is going to be 1, 2 in the pink. So bromine, or the bromo, is going to go first. So it's going to be, we put it all together, it's going to be 1 dash bromo dash 2 dash methyl cyclo and then propane, the A and E, because we have no functional groups attached to this. And our fourth and final one is going to be this one. Again, longest uninterrupted chain of atoms or carbons is this nice big triangle. This is our parent. We know that this is our cycloprop. So now we circle our branches. We have one here. And let's not forget our bromine. We have one here. So from here, it is since it is the only since this carbon is the only carbon that has branches attached to it, the one is automatically assigned here. So now for our branches, it's going to be methyl again, because it's a single carbon, and then bromo, because it is the single bromine. Now, with this one, it's not the same as this one where the carbon and the bromine were bonded together. They're separated. So instead of being 1 dash bromomethyl, in this case, it's going to be 1 dash bromo dash 1 dash methyl, because they're on separate branches, cyclopropane. Again, because we have propane. Again, because we have no additional we have no functional groups attached to this. And the bromo comes first before the methyl because comes before N in the alphabet. We go by alphabetical order since the branch numbers are the same. So that wraps up question number 2. Question number 3. Show that phenol has a more acidic proton than cyclohexanol. Explain why you why you examine why you are examining the proton in the comparison as opposed to any other hydrogen in the compound. So again, I went ahead and took the liberty of drawing, but ignore that for now. Let's not get too far ahead of ourselves. We have phenol, which is this one right here. And then we have cyclohexanol, which is this one over here. So cyclohexanol, uh, let's start with the phenol. The phenol, I did not know this off the top of my head. I had to go to, again, the functional group chart that is on page 2 of the chapter 3 notes that will be provided on the test according to the professor. So you can go on here and look for fentanyl, and it's on here under the oxygen containing compounds. It is the second one. So because of that chart, I know that this is what fentanyl, oop, not fentanyl, phenol looks like. And then cyclohexanol, oops, they have an OH. That's where the OL at the end comes from because the OH is alcohol. So that OH suffix goes to the name. So cyclohexanol, well, I know cyclohex is the ring of 6 carbons, and then the OL tells me that there is a alcohol attached to it. In this case, the OH is not a hydroxide, it is an alcohol. So that's how I establish that this is what these two molecules look like. Now, since we are examining the acidity of these molecules, we need to look at the conjugate bases. So for the conjugate bases, we now have molecules that look like this. We lose our protons, so we have an oxygen that looks like this, and we have an oxygen that looks like this. Well, since we have the same size molecule and the negative charge is on the same type of atom, in this case, an oxygen, we need to look at resonance structures. So when doing the resonance structures, we'll do the 1, 2, 3 method here, and one has to have a at least one pair of lone pairs, or at least one lone pair. And then in between 2 and 3, you have to have a pi bond, or also known as a double bond. So for fentanyl, we have 1, 2, 3. And this works because one has a lone pair, and 2 and 3 have a pi bond between them. When we go over here to cyclohexanol, we have if we do 1, 2, 3, there we have a missing pi bond. There's no pi bond there, so we cannot do a resonance structure. Even if we went 3 down here, again, there's no pi bond. So there are no resonance structures to cyclohexanol, meaning that the negative charge from uh from the proton being lost or given away cannot be displaced anywhere else. It has to be on this singular oxygen, which doesn't make for a very good base or a conjugate. It doesn't make for a very good conjugate base. That's not very stable in comparison to other molecules that can displace the negative charge. So phenol, phenol can displace this negative charge. Let's go ahead and go through all of its resonance structures. We have a lone pair that goes here to form a double bond or a pi bond, and this pi bond goes goes to become electrons over here on this carbon. So now this becomes a carbon with 2 electrons and a negative charge, and there is a double bond on this oxygen. And now we just keep repeating this process. We have 1, 2, 3. We have one thing of lone pairs that moves to create a pi bond, and this pi bond moves to create or breaks to create uh, lone pairs in a negative charge. So then we get lone pairs here in a negative charge, and this pi bond should be broken. And now we have a pi bond here. So now if we do 1, 2, 3, we have these lone pairs going here to make a pi bond, and this pi bond breaking to make um, lone pairs. Paste. So now we have a pi bond here, and we have lone pairs here. So if we were to do this again, it would be 1, 2, oops, forgetting our little oxygen over here, and then 3. And this repeats. The 3 cannot go here because there is no pi bond there. So the 3 must go back to the oxygen where the pi bond is. So these lone pairs form bond to make a pi bond, and this pi bond breaks to uh, create more lone pairs on this oxygen. So we have 4 different resonance structures for phenol and only 1 for cyclohexanol. Therefore, phenol is more acidic. And because it has a more stable conjugate base. The reason the conjugate base is more stable is because it's able to displace or disperse that negative charge over more atoms, in this case, every single atom in this molecule, and being able to disperse that negative charge uh, makes it more stable because that energy is spread out in a sense. In comparison to cyclohexanol, which cannot do that. So it's a very unstable conjugate base, which makes for a very weak acid. So fentanyl is the uh, stronger acid. Another To reiterate in a more concise way, phenol is more acidic because the conjugate base has more resonance structures, so the negative charge is displaced over more atoms, making it more stable, thus more acidic. So, now to answer the second part of this question is the asking why we're looking at the proton and not the other hydrogens. The reason we're looking at the proton is because the proton leaves behind two, not leaves behind two. When the bond with the proton with that hydrogen breaks, or with that proton breaks, it leaves behind its electron. So giving the molecule it was attached to a more negative charge. So moving on to question 4. Draw any two trisubcyclohexanes on 1, 2, 3, or 1, 2, 4 positions and show which is the more stable conformer. No repeats from other classmates. So I'm the only one doing this, so it doesn't matter. I found these two off of somewhere on the internet, and they fulfill the requirements because we have 1, 2, 3, 4, and then we have 1, 2, and 3. And the reason I know it's in that direction because if we went 1, 2, 3, 4, 5, the 4 is the smallest point of difference, and it asked for a 1, 2, 3, 4. And if I went from here, 1, that'd be 2, so this would be 3, and then 4. It didn't ask for a 1, 3, 4, and the 2 is a smaller point of difference. So yeah, that's why they're labeled like this. So to be able to tell which is the more stable conformer, we have to draw the chairs. With chairs, we have our axials and our equatorials. When it comes to checking which is going to be more stable, we want the larger functional group to be on the equatorials because it puts less strain on the overall molecule, which is good because that makes it more unstable. When we have it on the equatorial, it puts less strain, so it is calmer, which is what we want. So anything, any peaks on the chair go up. So those are going to be our axials, and anything that's concaved is going to go down. Same thing on this side. These are going to go up, and these are going to go down. So now for our equatorials, if the axial is going up, the equatorial goes down. So down, 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 down. Wait, oops. Ignore that. I totally was wrong. That's down. That one's down. This one is down. And then we have our ups. So if the equatorial is down, the axial is down, the equatorial is up. So it's going to be up, up, and up. Oop, up. And then same thing for the other side. It's going to be down, down, and down. Then axials are down, so equatorials are going to be up, up, and up. Now we also need to number uh our chairs. So I'm gonna do 1, 2, 3, 4, 5, 6, 6. Same thing on this side. 1, 2, 3, 4, 5, 6. So now we correspond the numbers to the axials or equatorials. The 3, 3, 8, the through this oh my goodness. The C3H6 is going down on 1 because it's the dashes, so it's away from us. So it's going to go here. For C2H8, it's going down on 2, so it's going to go here. Light squeeze. Okay. And then C4H9 is going to be up on 4. Now let's go over to this other one. We have C4H9 going down on 1, so it's going to go here. Cl on 2 is going up, so Cl goes here. Yes. And then bromine is going up on 3, so we have bromine here. So the first thing that we look at when we are considering stability of a conformer is the largest molecule. In this case, our largest molecule is C4H9, and we want that largest molecule, as I was saying before, on the equatorial. So in this case, any of the blue lines that I drew on these chairs. This is why it helps to color code. Thankfully, both of these C4H9s are already on the equatorials, so we don't have to worry about inverting it or flipping it. But since these are the same function group of the C4H9, they're the same size. So since those are the same, we now need to look at the other two function groups that are on this chair. When we look at, again, we want the bigger ones on the equatorials, so the smaller ones are less troublesome on the axials. So we have C2H8 on an axial, and we have C3H8 on an equatorial. Over here, we have bromine on an axial and chlorine on an equatorial. So bromine and chlorine are both significantly smaller than C2H8 and C3H8. If you look at your periodic table, they're all not too far off in size. Well, kind of. If you're looking at like atomic mass, but also the molecular size of this is much larger. All your hydrogens. I don't even know where all those hydrogens go. Wait, yes, I do. Nope. Can you have? Did I write something down wrong? I did. Oh my goodness. Huge error on my part. This is supposed to be H6. I have it written correctly on my paper. I just did not catch that when doing this video for y'all. I am so sorry. Anytime I said C2H8, did mean C2H6. I think I corrected all of them. So C2H6, you have these much larger molecules than you would just a single bromine or a single chlorine. So the bromine versus the C2H6 is much less puts much less strain on the chair. And since it puts less strain on the chair, it is the more stable cyclohexane. Thank you for watching.